Suppose an MTSU basketball player makes 60% of his free throws. His coach feels this could be improved by changing his throwing motion and orders him to go through a 2-week training to do this. After the training is over, the player makes 16 out of his next 24 free throw attempts. Is this sample proportion evidence that the training technique worked? So step 1, let's state the null hypothesis. So this is symbolized HO. This will always involve the population parameters, in this class P and mu. So never ever will this involve sample statistics. So in this example, we have HO, P equals 0.6. So the proportion of free throws is 0.6. We often convert those percents to decimals, because that's how they're often put into technology. Step 2, let's state the alternative hypothesis, symbolized HA or sometimes H1. Here, HA, P is greater than 0.6, so we're hoping that this technique improved his free throws. And then step 3, let's determine the model that's going to be used. We have one proportion. This is called a 1 proportion Z test. So while this is mainly a StatCrunch video, I'd be remiss if I didn't mention that these tests, almost all of them will have assumptions that go with it. Be honest, normally on textbook problems they are met, but you still need to mentally go through them. So the simple random sample is independent. So we often have to assume independence. 10% condition. So this is less than 10% of all potential free throws. So we can't have the sample be too big. And then it needs to be big enough, right? So n times p has to be greater than 10, and n times 1 minus p has to be greater than 10. And so now in StatCrunch, I'm going to go to Stat, Proportion Stats. We have one sample, and this is with summary data. So in this problem, the number of successes, he made 16 out of 24. And we're testing this at 0.6. And the HA is going to be greater than 0.6. And you may want to do a p-value plot just so you can see this visually, what it looks like. And press compute. So we see that our sample proportion is about 67%, which is indeed greater than 60%. But how likely am I to get a sample proportion this large if the true proportion of free throws really is 0.6? That is, percentage really is 60%. Well, it's about 25%. That's what p-value is. So 25% of the time, I'll get a percentage this great, even if this null hypothesis is true. So I can't reject HO. So I fail to reject HO. There's not enough evidence that his free throw percentage has improved. And we can press this little next button here and see this shaded out. Clearly, the area under the curve here is greater than 0.05. It's about 25%. Well, what can this guy do to make his case? Well, he could increase his free throws, right? So let's do that. Let's go ahead and restate the problem. So let's frame it this way. Suppose that after the next several games, the coach calculates the player's free throw percentage. The player makes 100 out of 150 free throw attempts. Should the coach be convinced that his free throw percentage has improved from the 60%? So in StatCrunch, I'm just going to go back here to edit, and let's edit this. It's now going to be 100 successes out of 150. Hypothesis test is the same, and press compute. So even though the sample proportion is the same, 100 divided by 150 is 0.666 or 67%. Notice our p-value is significantly lower. It's 0.0478, which is less than 0.05, which is generally set at our alpha level if none is stated. So we would reject the null hypothesis that his free throw percentage is 60% and say, it's greater than 60%. We can click this next button here and see this drawn out. Our z-stat 1.67, so we're 1.67 standard deviations away from the mean. P-value, the area that's shaded here in red, is 0.0478.